Sometimes a revolution doesn't start with a bang, but with a research paper. Back in 2017, a paper was published that, well, it didn't exactly make headlines, but it quietly lit the fuse on the whole AI explosion we're living through right now. It's called Attention is All You Need, and it is the foundational blueprint for pretty much all the generative AI we use, from ChatGPT to Midjourney. All right, let's get into it. So to really get why this paper was such a game changer, we have to understand the problem it was trying to solve. Look at this sentence. How does a machine know that the cat is the thing that sat? Look how far apart those words are. For an AI, keeping track of these connections across long sentences was a massive, massive challenge. Here's how we're going to break this down. First, we're going to look at the old, kind of slow way AI used to work. Then we'll dive into the brilliant breakthrough they called attention. After that, we'll peek under the hood of the transformer architecture it created, and finally, we'll see the incredible results that kicked off this whole new era for AI. So before 2017, what was everybody doing? Well, the top models were something called recurrent neural networks, or RNNs for short, and they had a really big fundamental problem. See, RNNs had to read a sentence sequentially, just one word at a time, from left to right. Imagine trying to read a whole novel, but you're only allowed to look at it through a tiny little peephole, one word at a time. You'd have to remember what happened at the beginning of the chapter by the time you got to the end, right? It gets really hard, really fast. And this one word at a time approach, what the paper calls its inherently sequential nature, created two huge headaches. First, since it has to process word 1 before it can even look at word 2, you can't parallelize the work. You can't just throw more computers at the problem to speed it up. It's a bottleneck. And second, by the time the model gets to the end of a long sentence, it can actually start to forget what happened at the beginning. This made learning those super important long-range connections, like our cat that sat, incredibly difficult. So, the authors of this paper proposed something kind of radical. They asked, what if, instead of reading one word at a time, the model could just see and process the entire sentence all at once? This line right here from the paper's abstract, this was a shot across the bow of the entire AI world. They weren't just trying to improve the old method. They were saying, let's just throw it out completely. And the key to their whole new system was a mechanism called self-attention. So what the heck is self-attention? Well, think of it like this. The old RNN method was like a conference call where everyone has to speak one after another. Self-attention is like putting everyone in the same room for a meeting. Now, when the model is processing the word sat, it can instantly look across the room at the word cat and go, aha, that's the important connection here, and give it a high attention score. Every single word can look at every other word at the exact same time. This self-attention mechanism is the powerful engine inside the brand new architecture they introduced, the transformer. So let's pop the hood and take a quick look at a few of its most important parts. Now, the transformer uses a pretty standard encoder-decoder structure. That's just one part to read the input and another to generate the output. But the real magic, the secret sauce, is in how it uses attention, with two key innovations, something called multi-head attention and another called positional encoding. The authors figured that just looking at a sentence from one perspective might not be enough, so they created multi-head attention. It's kind of like having a team of experts all analyzing a sentence at the same time. One expert might be focusing on grammar. Another is looking at semantic meaning, what the words actually mean. And a third might be looking at the relationships between words. By getting all these different viewpoints at once, the model develops a much richer, more multifaceted understanding of the text. And in their base model, they didn't just have one or two of these attention heads or experts. They had 8 of them, all working in parallel, each learning to focus on different parts of the language. But wait a minute, you might be thinking, if the model sees all the words at once, how does it know their order? The cat sat on the mat is totally different from the mat sat on the cat. The solution is positional encoding. It's a really clever bit of math that basically stamps each word with a little signal that says, hey, your position number 1, your position number 2, and so on. It's how the model keeps the word order straight. So we've got this brand new architecture, but was it actually any better? On paper, the theoretical advantages were just staggering. This table from the paper really says it all. With self-attention, the model can connect any 2 words in the sentence in a single step. For an RNN, though, the path gets longer and longer the farther apart the words are. And because self-attention isn't sequential, it's massively parallelizable. You can just throw more computing power at it, and it gets faster. So the big takeaway here is this. The transformer promised to be way faster to train and way more powerful at understanding context. I mean, it was a theoretical knockout, but they still had to prove it could work in the real world.
And oh boy, did they prove it. The researchers tested their new model on the super difficult task of machine translation, and the results, well, they were nothing short of a paradigm shift.
On a standard translation test, the transformer didn't just beat the best models out there, it blew past them by over 2 Blue U points. Now, blue is just a score for how good a machine translation is, but in that field, a 2-point jump is a massive leap in quality. It was a brand new, state-of-the-art, overnight. And you can see the jump right here. The best previous systems, these really complex models, they were struck at a score of around 26.4. The transformer, as just a single model, shot all the way up to 28.4. It was a clear, decisive win. But this is the most stunning part. The transformer got these amazing results while using a tiny fraction of the computational power to train. We're talking almost 50 times more efficient than the previous best model. This wasn't just better, it was smarter, faster, and cheaper. This combination, way better performance and radical efficiency, is what truly changed the game. It made building these powerful, large-scale AI models accessible to so many more people, and that directly led to the generative AI tools that we all use every single day. The paper's title was a bold claim, but it turned out to be true for language. And it leaves us with a final, really tantalizing question. The authors themselves said they plan to apply this to images, audio, and video. So, as we're seeing today, the revolution they started with text is really just the beginning. The real question is, what's next?